Assalamu alaikum dear students. This is our third lecture of group 3-2. So today we will discuss conjugacy classes of symmetric group essay, and I'll try to elaborate a computational technique to find number of conjugacy classes and the order of every conjugacy class in Sn, right? So before giving the details of the concept, I want to give one definition first. Cycle type of permutation. What is a cycle type of permutation? Suppose a permutation alpha, of course, alpha belong to Sn. Alpha belong to Sn. Alpha belong to Sn, of degree n. Since alpha belong to Sn, of course, we are finding Sn over a set containing n objects, right, of degree n. Is decomposable into r disjoint cycles of lengths k1, k2, k3, kr, where ki are greater than equal to 1 means that we need to keep in mind cycles of length 1 also, right? For each I, where ki of course is an integer, because the length of a cycle is an integer, always is an integer. A cycle may be of length 1, maybe of length 2, of length 3, and so on and so forth. That's why these ki's are in fact the lengths of the cycles which are appearing in the decomposition of alpha. You know very well in group 3-1 you have learned this thing that you can decompose a permutation into disjoint cycles, right? Okay, so then this R tuple, k1 comma k2 comma k, is called the cycle type of the permutation alpha. This is the cycle type, cycle structure of that permutation alpha. So we will say that alpha is of the type, right? Means that this alpha contains a cycle of length k1, a cycle of length k2, and cycle of length k3, and so on, a cycle of length kr, where of course these are integers, right? So you can decompose any permutation alpha into disjoint cycles. You know very well, it's a very simple result. You can find in almost all books of group theory. And here remember, the sum of these lengths k1 plus k2 plus k3 so on plus kr should be n, right? Then we call that alpha is of the type, or this one is the type of alpha, cycle type of alpha. So suppose you have a permutation 1, 2, 3 up to 12. We are finding permutations on first 12 integers, and this is one of the element of S12. Of course, alpha is an element of S12. This belong to S12, right? And if you think on this, you see 1, 2, 2, 1. It's a cycle of length 2. Then 3, 4, 4, 5, 5, 3. The cycle of 3 lengths. Then 6, 6 is the fixed element or point. You also call this is a point. Okay, not a cycle, it's a point. A cycle of length 1 is called a point. Then 7, 8, 9, 10, 7 to 8, 8 to 9, 9 to 10, 10 to 7 is a cycle of length 4, a cycle of length 2. So what is the cycle type of this permutation? This 2, then 3, then 1, cycle of length 1. It's a point. And then 4, cycle of length 4, and then cycle of length 2. This is the cycle type of this permutation alpha, which was an element of S12. Okay, remember? So note that 2 plus 3 plus 1 plus 4 plus 2, this should be 12. That's why we are considering points as well. If you will remove this point from this decomposition, then some is difficult to find sum 12. That's why we need to count points as well to find this sum, which is equal to n, right? So remember, what do you mean by a type? Type is actually an R tuple where this tuple containing the size of cycles appearing in the decomposition of alpha, right? Okay. So now let's see the conjugacy classes of S3 and then S4, and then we will try to generalize a formula to find the conjugacy classes of Sn. Okay. Okay, what is S3? You know very well. S3 is, you can find S3 as S3. This is 1 and 1, 2. Here 1, 2, 3. 1, 2, 3. So 1, 1, 2, 3. This is cycle of length 1 or point. So all are, you know, this is identity and you can label it's 1, no problem. So then 1, 2, and then 1, 3, 1, 2, 1, 3, and then 2, 3, this is 2, 3. Then after you have, these are the transposition, cycle of length 2 is called a transposition. Then of course 1, 2, 3, 1, 2, 3, and you can replace these two to get its inverse 1, 3, 2. You know, this is an element of order 3. Of course, this is an element of order 3, the rotation, and these are the fluxions, elements of order 2. So to find the conjugacy classes, as you know that center of S3 is equal to just 1. The identity element is the center. You know, in last lecture we have discussed the center of Dn as well. This is of course isomorphic to D3. And then what should be the conjugacy classes? There should be one conjugacy class. Then you have, these are the transposition. So different type of cycles. So 1, 2, 1, 3, and 2, 3. Right? This is the second class, and also you know that reflections are appearing in one set. We can find this. This is the element of center. That's why it's a self-conjugate element. And you know that a self-conjugate element contains exactly one element in its conjugacy class, which is the element itself. That's why this one. And for 1, 2, I can find 1, 2, the conjugate with 1, 2, and 1, 2 inverse. You say this is 1, 2, and then 1, 2 with 1, 3, 1, 3, 1, 3 inverse. This is equal to 1, 2, 1, 2, 1, 2. You know, this is the transposition, so it has its own inverse, the 1, 2, and you multiply 1 mapped onto 2, 2 mapped onto 1, and 1 mapped onto 2. That's why 1 mapped onto 2. You can start from here. We want to see the image of 1. 1 is mapped onto 2. Right, start from here. Then come here. 2. 2 is mapped onto 1, and then 1 is mapped onto 2. So in fact 1 is mapped onto 2. Now you need to see that. What is the answer of this 2? 2 is mapped onto 1, 1 is mapped onto 2, and then 2 is mapped onto 1. So 2 is mapped onto 1, that's why it's closed. So it's a transposition. Similarly, you can see this is 1, 3, 1, 2, 1, 3. You see 1, 3, 3, 3. Here you cannot see 3. So 1 is mapped onto 3, and 3 is mapped onto 3 because 3 is missing from here. It's a point. 3 is mapped onto 3, and 3 is mapped onto 1, right? So 3. So 1, first you see 1 is mapped onto 3, and 3 is mapped onto 3 is mapped onto 3, and 3 is mapped onto 1. So this is 1, and then 2. 2 is mapped onto 2, and 2 is mapped onto 1. 1 is mapped onto 3, then 2 is mapped onto 3. So now what is answer of 3? 3 mapped onto 1, 1 mapped onto 2, and 2 mapped onto 2. So 3 mapped onto 2. That's why this is 2, 3. This is in fact 2, 3. You know, with the multiplication of identity, we are getting the same answer. Then with this 2, 3, 1, 2, 2, 3 inverse, we want to prove that this is the conjugacy class, right? And this is equal to 2, 3, 1, 2, 2, 3, because you know this is a transposition and has on inverse, that's why 2, 3. Now see, what is the answer of 1? 1 is mapped onto 1, here 1 is missing in this. 1 is mapped onto 1, 1 is mapped onto 2, 2 is mapped onto 3, so 1 is mapped onto 3, right? Now see the answer of 2. What is 2? Of course we should see 3 now. 3 is mapped onto 2, 2 is mapped onto 1, 1 is mapped onto 1, so 3 is mapped onto 1, so this is closed. Now 2, you see 2. 2 is mapped onto 3, 2. What is the value of 2? 2 is mapped onto 2, 2 is mapped onto 3, and 3 is mapped onto 3. Here 3 is missing, so it's a point. 3 is a fixed point. Then 3 is mapped onto 2, so 2 is mapped onto 2. This is equal to 1, 3, right? Then of course you have to multiply this 1, 2 with the help of this one as well and this one also. So what is 1, 2, 3, 1, 2, 1, 2, 3 inverse, and you know that you can find its inverse. You can replace domain and range to get its inverse. This is equal to 1, 2, 3, and 1, 2, and this is 1, 3, 2. Now you see, what is the answer of 1? 1 is mapped onto 3, 3 is mapped onto 3, and then 3 is mapped onto 1, so 1 is mapped onto 1. What is the value of 2, 3? Start from 2 is mapped onto 1, 1 is mapped onto 2, 2 is mapped onto 3, so 2 is mapped onto 3, this is 3. What is the answer of 3? 3 is mapped onto 2, 2 is mapped onto 1, and 1 is mapped onto 2, so 3 is mapped onto 2, this is closed, so this is equal to 2, 3, right? And lastly, we have another element 1, 3, 2, so 1, 2 into 1, 3, 2, so 1, 3, 2 inverse, and you know that this is equal to 1, 3, 2, 1, 2, and 1, 2, 3. You solve the answer of 1, 1, 2, 2, 1, 1, 3, so 1, 3, 3, 1, 1, 2, 2, 1, so 3, 1, that's why. Now 2, 2, 3, 3, 3 is fixed, and 3, 2, so 2, 2, this is clear, this is 1, 3. So these are the elements for corresponding this 1, 2, 1, 2, 1 is this, 1 is this, 1 is this, 1 is this, and 1 is this. You see, these are the transposition. So this is the conjugacy classes. You know that to find the conjugacy class, you know that we write like G, alpha, G inverse. These are the conjugate elements, and here alpha was 1, 2, alpha was 1, 2, and you have very G belong to S3. G was an element of S3, So that's why we have seen behavior of all elements with 1, 2, and you have seen that 1, 2, 2, 3, 1, 3, 2, 3, and 1, 3. These are the 1, 2, 1, 3, 2, 3. These are the three elements for the conjugacy class of 1, 2. This is also conjugacy class of C1, 3. This is also conjugacy class of C2, 3. So you can write this as well. This is in fact C1, 2. Also you can say C1, 3. Also you can say that 2, 3. So these three classes are identical. Right. Next, 1, 2, 3. You can find the class of 1, 2, 3. How can you find? Is that so for this one, I have no ability to write its conjugacy class. So what was the conjugacy classes? C1 was 1 and C12 was 1, 2, 1, 3, 2, 3. And you know this is 1, 2, 3. 1, 2, 3 does not belong to center of S3. Since 1, 2, 3 is not elemental of S3, so it is not self-conjugate. And since it is not self-conjugate, so in its conjugacy class there must be more than one element. There must be more than one element, because you know that an element is self-conjugate. Then it is a central element. So since this is not the central element, so it is not self-conjugate. So because this must contain another element which must be this. So that's why the third conjugacy class is C. The conjugacy class C1, 2, 3 must be equal to 1, 2, 3 and 1, 3, 2. Look at this. There is no problem. You can enjoy the definition of self-conjugate, because 1, 2, 3 is not an element of this, and since you have only two elements remaining, and this element cannot have a single element in its conjugacy class, because this is not a self-conjugate element. That's why you must have to enter one more element in its conjugacy class. And since you have only one element remaining, that's why both are appearing in one conjugacy class, right? So these are the three conjugacy classes for S3. Now you can list the conjugacy classes of S4 as well. So okay, for S4, in fact this is 1, 2, 3, 4. So you can write the element of S4. First is the identity, then so 1, 2, 1, 3, 1, 4, then 2, 3, 2, 4, then 3, 4. These are the transpositions, right? You just write the transposition 1, 2, 1, 2, 1, 3, 1, 4, 2, 3, 1, 2, 1, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, then 3, 4, 3, 4. Okay, these are the transposition. Then you can have elements which is a product of these two transposition. So these could be 1, 2, 1, 3, 1, 2 disjoint, which can be expressed, those permutations which can be expressed as a product of disjoint cycles, right? So this could be 1, 2, to keep it disjoint we must have 3, 4, 3, 4, this is also, of course here 5 is fixed element. So 5 is the fixed element, its cycle type is 2, 2, 1, so no need to write again and again. You know that these are the four elements, 1, 2, 3, 3, 4. Sorry, this is S4, not S5. Sorry, this is S4. So for S4, 1, 2, 3, 4, yes, 4 elements are complete, right? So 1, 2, 3, 4, 1, 2, 3, 4, then you see 1, 3. If you take 1, 3, then disjoint 1, 3, this is 2, 4, this is 2, 4. If you take 1, 4, you have 2, 3. Because if they are disjoint, then their union is the entire 1, 2, 3, 4. You see 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So these are the 3 elements, right? Okay. Then you can write the elements of cycle 3. So these are the 3 elements. Okay. Then 1 to 3 elements of cycle 3. This is 1, 2, 3, and there could be, you see, you just fix 1, 1, 2 and combine this. 1, 2, 3, 1, 2, 3, 1, 2, 4, and then leave 1, 2, you fix 1, 3, and this is 1, 3, 4, yes, then leave 3, so you have this 2, 3, 4. So these are the elements 1, 2, 3. Then, of course, since it's a cycle, it's a group, you need to write its inverse. So the 1, 2, 3 inverse is 1, 3, 2. Okay. Then this is 1, 2, 3. Then 1, 2, 4. 1, 2, 4. Of course, its inverse is 1, 4, 2. 1, 4, 2 is the inverse of this. And then this is 1, 2, 4. 1, 2, 4. And leave 2. This is 1, 3, 4. So 1, 3, 4. And write its inverse. This is 1, 4, 3. Then lastly, you have 2, 3, 4. 2, 3, 4. And its inverse is 2, 4, 3. Right. These are the 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 elements. Okay. Then write lastly the permutations of cycles of length 4. These are 1, 2, 3, 4. Okay. To write this, you keep 1 as fixed, and this is 2, 3, 4. And how many permutations we can find with the help of 3 elements? 6. So you can apply the formula for S3 on these 2, 3, 4 to get these 6 permutations, right? So this is 1, you fix 1, and we are fixing 2. This is 4, 3. Then 1, instead of 2 write 3. If you write 3 here, of course you are getting 2, 4, and 3 fix, you replace 4, 2, and then you write 1, instead of 2 write 3, 4, you will get 2, 3, and then lastly you write 1, 4, and you replace this 3, 2. Okay, so these are the 1, 2, 3, 4, 5, 6 elements. 6 and 8. 14, 14 and 3, 17, 17, 1, 18, 18 and 1, 2, 3, 4, 5, 6. These are the 24 elements. And of course, we are writing in such a way that all are appearing in different form. Their cycle type are same, right? So because these are the cycle, you can never decompose further. Okay, that's why these are in fact the different types. So these are the conjugacy classes. How many conjugacy classes? 1, 2, 3, 4, 5. So S4 has 5 conjugacy classes, right? S4 has 5 conjugacy classes, and you see that in this conjugacy class you have 1 element. In this conjugacy class you have 1, 2, 3, 4, 5, 6. 6 elements. In this conjugacy class, we have 1, 2, 3, 3 elements. In this conjugacy class, you have 1, 2, 3, 4, 5, 6, 7, 8, 8 elements. And in this conjugacy class, you have 1, 2, 3, 4, 5, 6 elements. So what is the class equation? Class equation is 24 is equal to 1 plus, that is 1 plus 3 plus 6 plus 6 and then plus 8. You saw 12 and 4, 16, 16 and 24. So 24, this is in fact S4 order. And if you write in one set, you can find these are the elements of S4. But this is not an easy way for S5 and S6 and S7 and S8 and so on and so forth. We want to find some computational technique, some other technique. This was the simple definition technique. Okay. Now I want to give you some more definitions to establish another technique to establish these conjugacy classes through computational technique. Okay. So we need to know a little number theory and a recursive formula to find these conjugacy classes, and you know that this formula can be found from elementary number theory books, the formula for integer partitions, right? So what's that? I am just telling you. Okay. So we can say that we want to give a definition. Pn. What is Pn? Number of unordered integer partitions of an integer, of course positive integer n with P1n is equal to 1. What is this? I will tell you. Okay, so here P, what is P1? This is 1 because you have only one way. 1 can be written as 1. Number of partition. Can you find the number of partition of an integer? I am giving you some example to understand the concept. See, so P2. What is P2? 2 have 2 partition, and one is 2 is equal to 2 and the other 2 is equal to 1 plus 1. So P2 is equal to 2, right? Then what is P3? P3, see, 3 is equal to 3, 1, 3 is equal to 2 plus 1 and then 3 is equal to 1 plus 1 plus 1. So you have 3 partitions for, this is 3, and then P4, for P4 you have 4 is equal to 4, then 4 is equal to 2 plus 2, then 4 is equal to 2 plus 1 plus 1, then 4 is equal to 3 plus 1, then 4 is equal to 1 plus 1 plus 1 plus 1. So how many partitions? 1, 2, 3, 4, 5. We have 5 partitions. So P4 is equal to 5. Similarly, you see that P. Okay, now see, since symbol Pn, number of unordered integer partitions of any positive integer n. Leave it. This is I don't want to use this now. After a little discussion, I will introduce what is this. Okay, so P1, number of partitions. So 1 can be written as only by the one way. 1 is equal to 1, right? So P2, 2 can be written by 2 ways. 2 is equal to 2 and 2 is equal to 1 plus 1. So you have 2 partitions for 2, right? Okay, so 3 is equal to 3 and 2 plus 1, 1 plus 1 plus 1. So these partition, you can write these partition as, this is one partition of 3, this is one partition of 3, and this is another partition 1, 1, 1. Okay, we are going to cycle type. I'll try to synchronize these two at the end. So see, these are the three partition for 3, 3, 2, 1, mean 1 plus, if you add up these two, sum should be 3, right? So we define this symbol Pn, number of unordered integer partitions of any positive integer n, which side at the sum of its parts should be n, right? Okay, so we cannot find its any implicit formula, but we have some explicit formula, but we have some implicit, recursive formula. Okay, so by using that recursive formula, we can establish Pn corresponding to any n. So what is that formula? First we will discuss that formula, then we will try to link with Sn. Okay, the formula is so Pkn, formula is Pkn is equal to Pkn minus k, Pkn minus k plus Pk minus 1 and minus 1, where we have some conditions. Pkn would be equal to 0 if k is greater than n, and secondly P1n is equal to 1 for all n, and note Pn is equal to summation Pkn, where k is from say 1 to r. Okay, sorry, 1 to n, not r, because here n, 1 to n. Okay, let's try to find P5, because we want to discuss conjugacy classes of S5. So to discuss conjugacy classes for S5, we take n is equal to 5, and from here, what is Pk5? This is equal to Pk 5 minus k plus P k minus 1, 4, right? And what is Pn? Here P5 would be equal to summation Pk5, k is from 1 to 5, and P5 would be equal to P15 plus P25 plus P35 plus P45 plus P55. Okay, so we need to find P15, P25, P35, 45, 55, right? So first of all we will find P55, right? And you know P15 is 1, P1n is equal to 1 for all n. So you know P15 is equal to 1. Here clearly note P15 is equal to 1. You have calculated P15. Now you can find P25. Put k is equal to, k is equal to 2. So P25 is equal to, k is equal to, k is equal to P2 5 minus 2, this is 3 plus P2 minus 1, P1 4, and you know that P2 3, and this one is greater than this, because Pkn, if k greater than n, no, this is k not greater than, p less than 2 3, so this is 1, we will find P2 3, say this is 1, now P2 3, P2 3, here k is equal to 2, n is equal to 3, right? Here k is equal to 2, n is equal to 3. To get what is P2 3? Put here P2 3. P2 3 is equal to Pk P2 3. N minus k, 3 minus 2, this is 1, right, plus Pk minus 1, 2 minus 1, this is P1, n minus 1, 3 minus, P1 2, this is P1 2, and you know this tends to 0, P2 1, you know Pkn, if k greater than n, it's 0, so k greater than n, here k greater than 1, this tends to 0, so P1 2 by P1 n is equal to 1, this is equal to 0 plus 1, which is equal to 1, put here, putting in 1, we get P25 is equal to, what is P23? P23 is equal to 1 plus P14, this is 1, n is equal to 1, so P14 is equal to 1, this is equal to 2, so P25 is equal to 2, P25 is equal to 2, okay. Next, P35, we will find P35. For P35, now I can find directly when k is equal to 3. This is P35, this is equal to P32, 5 minus 3, this is 2, plus P, k is equal to 3, this is P2 and 4, this is P2 4. Okay, so we have calculated this is equal to P15, P15 is equal to 1 plus P25 is equal to 2 plus, what is this? P35. I am going to find P35. P35 is equal to P32 and then P3 minus k, 3 minus 1, this is 2, 4. And you know 3 is greater than 2, this tends to 0, which is equal to P24. Now P24 is, this is equation number 2. So P24, put here P24. P24 is equal to P2 and 4 minus 2, this is 2 plus P4 minus 1, this is 3, and 4 minus this is 3. P24, this is P24, we write 2, 4 minus 2, this is 2, and then P2. So here 2 minus 1, 1, this is 1, this is 1, 4 minus 1, this is 3, P1 3, Now P2 2 plus P1 3, and P1 n is equal to 1. This is P3 5. P3 5. This is P3 5 is P3 2 plus P2 4, and then P2 4 is equal to P2 2. What is P2 2? P2 2. We have no P2 2. So this one is P1 3 is 1. This is equal to P2 2 plus 1 number 3. Now you need to find P2 4. 2 2. So P2 2. Put here again P2 2, which is equal to P2 and 2 minus 2 n minus k, P2 2, P2 0 plus P2 minus 1 1, this is P1, and 2 minus 1 is 1, P1 1, and this tends to 0 because 2 is greater than 0, and P1 1 is equal to 1, so this is equal to 0 plus 1, which is 1, put here in 3 to get, so P3 5, P2 4 is equal to P2 2, P2 2 is 1, 1 plus 1, which is equal to 2, put in 2, so P3 5 is equal to 2, yes, this plus 2, plus. So we have found that P3 5 is equal to 2, yes, P3 5 is equal to 2. Then we need to know P4 5 and then P5 5. Okay, what is P? Similarly, if you find P4 5, this is equal to, you will find here P4 5, this is 4 1, 5 and 4, and is 5 and P4 1 plus P4 minus 1 3 and 5 minus 1 P3 4, and this tends to 0, which is equal to P3 4, 4 5 3 4. Similarly, P3 4 will be equal to P2 3, and P2 3, P2 3, and similarly P2 3 would be equal to P1 2. P2 3 would be equal to 1 2, and this is 1, so put here and then here, this means that this implies P4 5 is equal to P3 4 is equal to P2 3 is equal to P1 2, which is equal to 1, so this implies P4 5 is equal to 1 plus 1, and lastly P5 5. We can find this as well, P5 5 P5 5. So from here you find P5 1, of course this tends to 0, plus P4 4, and if P, this is equal to P4 4, and similarly P4 4 will be equal to P3 3, this would be equal to P2 2, this would be equal to P1 1, which is 1. So this implies P5 5 would be equal to 1. Yes, this is 1. So this is the class equation, or say P5. So P5 is equal to 1 plus 2 plus 2 plus 1 plus 1. So there are 2 plus 2, 4, 5, 6, 7. There are 7 classes. There are 7 classes. So there must be 7 conjugacy classes. I just want to tell you again how this works. Okay. What do you mean P1, 5? It means partition for 5 with the help of integer 1 and lower. So this is 1, and this means that 5 have only one way, so 5 is equal to 1 plus 1 plus 1 plus 1. This is the only way, plus 1. Because sum should be 5 with the help of 1 or lower integers. Now P52 is equal to 2. This means that sum should be 5, which can be calculated with the help of integer 2 and lesser integers. So 5 can be written as 2 plus 1, and secondly 5 can be written as 2 plus 1 plus 1 plus 1. So these are the 3 P25. Okay, then P35 is equal to 2, mean sum should be 5 with the help of 3 and lower integers. This is 2. So you see here again 2. One is 5 is 3 plus 2, and other 5 is 3 plus 1 plus 1. 3 and lowers. 3 must be the member. So 3 plus 2 could be 5, and 3 plus 1 could be 5. There is no other way with the help of 3. Either 3 can be added to 1 plus 1 to get 5, or 3 can be added to 2 to get 5. So these are the only 2 ways. Right. Next is P45 is equal to 1. Mean you want to find 5 with the 4 or lower integers. So you have only one way, which is equal to 4 plus 1. There is no other way, because 4 plus 2 is 6, 4 plus 3 is equal to 7, and 4 plus 4 is equal to 8. So you have 4 and 1, only one combination. Similarly, P5 is equal to 5 is equal to 1, mean sum with the help of 5 or lower integers. So you know 5 is equal to 5. This is the only one way. Okay. So these are the possible calculations, right? So what does it mean? That how can you write the elements? This means that this has one way, the only one, which is the identity. So these are only one type elements, which is 1, you know. Then those elements which are containing whose cycle structure 2 to 1 mean which are containing transpositions, and second transposition, then one is the point. So its structure is 1, 2, 3, 4 and 5, like this. You write 5 or not, we are not concerned, because it's a point, it's a fixed point, you can leave it. So I can write this, the structure like this simply, 1, 2, 3, 4. And then 2, 1, 1, another structure is, this is 2, 1, 1. So 1, 2 and 1, 1, 1. So you know this is kind of 1, 2. No need to write 1, 1, 1, because identity, if you multiply with identity, you are getting nothing, right? Except the 1, 2 itself. So that's why this 2, 1, 1 can be 1, 2. So 1, 2 type elements, right? One element of this type and one element of this type. These are the different types of permutations in S5 we are finding, right? And this is the computational technique. So from here you have 1, 2, 3. One cycle is of 3 type and the other is 4, 5. These types of cycle, we can find that how many cycles of this type appearing in that conjugacy class, and also we can find the how many types of elements are appearing in this conjugacy class. You can find the order of that conjugacy class, and also this and this. And lastly, there is another 5 3 1 1. So this is 1 2 3 only. It means that cycle of 3 types are appearing in 2 different conjugacy classes. Few are here and few are here, right? But with a transposition. So these are 1 2 3 cycle of 3 types here, appearing here, and then you have 4 1. So these are the cycle of the type 1 2 3 4 and 1. Okay, no need to write 1. This is 1 2 3 4. Okay, it's all right. And then 5, you have cycle of the type 1 2 3 4 5. Okay, so how many conjugacy classes there in S4? 1 2 3 4 5 6 7. So you have 7 type of elements, and remember there is a very popular theorem you can find in all books that 2 permutations are conjugate to each other if and only if they are of the same type or they have same cycle type, right? So it's a very well known. So it means that all permutation of the type will go in one conjugacy class, and all permutation of the type will go into one conjugacy class. All permutation of the type will go into one conjugacy class, and all permutation of the type is appearing in one conjugacy class, and similarly all permutation of the type is appearing in one conjugacy class. And then we also can find that how many conjugacy classes you have calculated the class equation. You can find the class equation, right? How can you find the class equation? Okay, you can also find the class equation. Now we can find the number of conjugacy classes in this way. So there are 7 conjugacy classes. There are P5 is equal to 7. If P5 is equal to 7, then there are 7 conjugacy classes in S5. Similarly, so since P5 is equal to 1 plus 2 plus 2 plus 1 plus 1 is equal to 7. So there are 7 conjugacy classes. So number of conjugacy classes in Sn is equal to number of unordered partitions Pn, right? Similarly, you can find for S4, P4 would be equal to P1, P14 plus P24 plus P34 plus P44, and you have all these calculations. P44 was P14 is equal to 1, and P24 you have this 24 is equal to 2, and P34 you have calculated 34. What was 34 in the last example? P34 was it was it was 1. P34 was 1. So this was 1 and this was 1. So 2 plus 1 plus 1 plus 1. There are 2, 3, 4, 5. 5. So P4 is equal to 5, mean that S4 has 5 conjugacy classes. We have discussed in my starting of this lecture. First at all, we have discussed the conjugacy classes of S3 and S4 manually. Now we are discussing these classes with the help of computational technique. So there are 5. And what is P3? For S3, you can find S3. This is P13 plus P23 plus P33. You know, we have calculated P13. This is P13 is 1. And what is P23? You have calculated P23. P23 is equal to, this is equal to 1. Yes, we found here somewhere. So this is equal to 1. So these are 3. So there are 3 classes for S3. So this is the computational technique to know the number of conjugacy classes in Sn. So what are the number of conjugacy classes in Sn is simply Pn. You should just find Pn. If you can find Pn, number of unordered partition of an integer n is equal to, in fact, the number of conjugacy classes in Sn. Now we can find order of every conjugacy class. What is that? Before this, I will write a formula first. So to find number of conjugacy classes, we have a formula.